Good morning everyone. My name is Dr. Vasanthi, Assistant Professor, Department of Mathematics from CPA College. Today we discuss about vector calculus. Vector calculus is a particular topic is eigenvalue problems. A matrix eigenvalue problems consider the vector equations. The first equation is Ax equal to lambda x. Here A is a square matrix and lambda is unknown scalar and x is an unknown vector. So lambda is called as a eigenvalue or characteristic value or latent value or proper roots or root of the matrix A, and x is called as eigenvector or characteristic vector or latent vector or real vector. So what are the eigenvalues? If A is an n cross n matrix and lambda is a scalar for which Ax equal to lambda x has a non-trivial solution, x belongs to R to the power of n, then lambda is an eigenvalue of A and x is a corresponding eigenvector of A. Therefore Ax equal to lambda x called the eigen problem for A. Note that we can rewrite the equation Ax equal to lambda x equal to A to the power of n or lambda x into x. Now lambda into in x minus ax equal to 0 or lambda into I x minus a into x equal to 0 comma x equal to 0 is the trivial solution, but our solution must be non-zero vectors called eigenvectors that corresponding to each of the distinct eigenvalues problems. Determine the eigenvalues for the examples of a equal to minus 5 to 2 comma minus 2. The second solution of these matrix is become so first we have to write the characteristic equations. Ax minus lambda equal to 0, a minus lambda equal to 0. So it can be written as Ax equal to 5 minus 5 to 2 comma minus 2 into the column vectors x1 comma x2 equal to lambda into x1 comma x2 is components. So solution of the eigenvalues is minus x1 plus 2x2 equal to lambda x1 and the other equation is 2x1 minus 2x2 equal to lambda x2. We have to solve these two equations. We get values of them a comma b. So this can be written in the matrix form a minus lambda into x equal to 0. Therefore ax minus lambda x equal to ax minus lambda into ix equal to a minus lambda I into x equal to 0. It gives the solutions. The second one is we see the homogeneous equation system. It has non-trivial solutions. So a vector A is looking for even only if the coefficients determinant is 0. Therefore d of lambda equal to determinant of a minus lambda equal to minus 5 minus lambda 2 into 2 the column matrix, the second row is 2 into minus 2 minus 2. So we have the value of the lambda value. Next we have to the characteristic determinant or expanded the characteristic polynomial and lambda x equal to 0 or determinant of x lambda equal to 0. The characteristic equation of the solution of this quadratic equations are lambda equal to minus 1 or lambda 2 equal to minus 6. These are the eigenvalues of A. Eigenvector corresponding to eigenvalue lambda 1 equal to 1 is a minus lambda I equal to 0. The second equation as an example is first row is we take a new matrix 2 cross 2 matrix minus 4 comma 2 and 2 comma 1 and the sub equations x comma y equal to 0 comma 0. Solving these two equations we get x equal to 0 and y equal to 0. These for eigenvector corresponding to eigenvalues lambda equal to minus 1 is e of x comma y equal to 0 comma 0. So for eigenvector space is e equal to 0 comma 0. Next we have to take the 3 cross 3 matrix, find the eigenvalues of A and find eigenvalues of a minus lambda I equal to 0. Then the determinant of lambda I minus a equal to or lambda modulus of lambda I minus a equal to 0. We get lambda minus 3 whole squared into lambda minus 1 equal to 0. Lambda equal to 1 has algebraic multiplicity 1 and lambda 2 equal to minus 6 has algebraic multiplicity 2. Eigenvector corresponding to lambda 1 equal to 3, therefore modulus of a minus lambda equal to 0. So we get a new matrix here x2 equal to r, then r belongs to capital R, the real valued function. Therefore minus 4x2 equal to 0 and minus 2x3 equal to 0. Now x2 and x3 equal to 0. Therefore the eigenvector corresponding to eigenvalue E of x comma x1 comma x2 comma up to xn equal to r of r comma 0 comma 0 up to 0. Therefore r is taking the common factor, therefore 1 comma 0 comma 0 belongs to R, eigenspace belongs to R. Now eigenvector corresponding to lambda 2 equal to 3, then we get a solution x2 equal to 0 and x3 equal to 0. Therefore eigenvector corresponding to eigenvalue, therefore E of r comma r of 1 comma 0 comma 0 such that r belongs to R. Now eigenvector corresponding to lambda 3 equal to 1, we get x2 equal to 0 and x1 equal to also 0. Therefore the eigenvector is also r of 0 comma 1 comma 0 belongs to R. So therefore R such that R. Thanking you.